When we watch a heavy steel I-beam bow under immense pressure, the metal appears to bend like a continuous, highly viscous fluid. But down at the atomic scale, solid metal doesn't flow. The bending we see on the outside is actually the cumulative result of trillions of microscopic, discrete mechanical shifts happening on the inside. To understand the math, we start with a perfect cubic single crystal. This diagram establishes our baseline, a rectangular block with defined dimensions. Within this volume, plastic deformation occurs through slip. A dislocation moves across a specific plane, shifting one layer of atoms over another. If we want to calculate why a suspension bridge stands or why a structural component fails, we have to mathematically connect that single atomic scale slip event to the observable yielding of the entire material. We define shear strain by a uniform physical displacement. An external force shears the top half of our crystal by a single atomic distance, the Berger's vector, b. The shear strain, gamma, is this displacement over total height, yielding roughly 1/10,000,000th of a percent. In reality, a single dislocation rarely crosses the crystal, moving only a partial distance x sub I before hitting an obstacle. To find total strain, we aggregate, multiplying the moving internal loads, n, by their average distance x bar, factoring in the Berger's vector over total area. Counting individual moving loads is practically impossible, so we use a continuous metric, dislocation density, or ρ. By defining ρ as the total length of dislocation lines per unit volume, our strain calculation becomes a direct mathematical function of dislocation density and average distance moved. To understand how a material bends under active stress over time, we differentiate our equation. Taking the derivative of the average distance gives us microscopic dislocation velocity, v. This yields the Taylor-Orowin equation. Macroscopic strain rate equals dislocation density times Berger's vector times dislocation velocity. If a solid material is deforming, it obeys this precise relationship. The rate of yielding is strictly bound by how many defects exist inside the metal and exactly how fast they are moving. Applying this to a macroscopic requirement, to achieve a barely visible 1% strain in a 1 cubic centimeter block, our equation shows we need 10 to the 8th power, 100 million, active dislocation lines. Pushing to 10% strain requires a billion. This creates a physical paradox. A standard metal straight from casting simply does not possess hundreds of millions of active dislocations. Spontaneous generation, like homogeneous nucleation, requires stress levels near absolute bond strength, never reached during standard loading. Other mechanisms like epitaxial mismatch or collapsing atomic vacancies do create baseline defects, but only yield a small fixed quantity. They entirely lack the capacity for exponential output. To survive the loading force without catastrophic brittle failure, the metal must contain an internal factory capable of manufacturing millions of defects on demand. The elegant solution to the billion-line paradox was formally identified in 1950. It is the Frank-Reed source, a crystallographic mechanism which functions as an infinite defect multiplication engine. This schematic details its initial state. We start with a single dislocation line, shown in orange, firmly anchored between two immobile obstacles in the crystal, marked A and B. When external shear stress pushes against this pinned line, the center bows outward. The required stress is inversely proportional to its radius of curvature. As the line bowing further, the radius decreases, meaning applied stress must continuously increase to push it further. This resistance hits a strict geometric threshold exactly when the line forms a perfect semicircle.
At this configuration, the radius is half the original pinned segment, and the required shear stress reaches its maximum possible value. Once the applied external load breaks past this peak stress barrier, the physics invert. The dislocation line begins expanding outward spontaneously, driving itself forward even if the applied stress drops slightly. As the loop balloons outward, the trailing segments are dragged and forced to spiral backward. These two ends, C and D, curve tightly toward each other. Because they curve from opposite directions, their internal stress fields carry opposite mathematical signs, causing physical attraction. When the opposing segments collide, they immediately annihilate at the contact point, pinching off the geometry. The immediate result is a completely independent, fully closed dislocation loop that detaches and continues expanding outward. Simultaneously, the interior segment snaps back into its original straight configuration between points A and B. The engine is fully reset. As long as the driving force is maintained, a single pinned segment rapidly repeats this exact process, emitting hundreds to thousands of complete dislocation loops every single second. This continuous multiplication permanently feeds the Taylor-Arawan equation, cleanly explaining how rigid materials manufacture the density required to survive extreme strain without fracturing. Generating 1 billion dislocations is only half the equation. Those defects must travel to cause deformation. But the interior lattice is densely packed with obstacles. As the Frank Reed source fires expanding loops, they glide across their slip plane until they encounter a barrier. The leading dislocation halts, and the hundreds firing behind it crash into its rear, creating a massive pile-up phenomenon. This gridlock forces extreme stress concentration onto the single lead dislocation. If N dislocations are trapped in the pile-up, the stress experienced at the very front is amplified to roughly N times pi. At the exact same time, because dislocations of the same sign repel each other, the compressed traffic jam generates a severe repulsive field, pushing backward against the direction of slip. This is called backstress. This backstress is the precise physical origin of work hardening. The material becomes physically harder to bend purely because its own generated defects are gridlocked and actively repelling new deformation. If the amplified pressure isn't relieved, the local stress exceeds the interatomic bond strength, initiating a microcrack that destroys the material entirely. To prevent immediate failure, dislocations utilize escape paths outlined here. Under sufficient stress, a screw dislocation executes a cross-slip, jumping to a different plane to bypass the blockage. Alternatively, in high-temperature environments, an edge dislocation can absorb vacancies and physically climb vertically over the obstacle. But even when dislocations navigate around these major barriers, they encounter static drag on the open slip plane. Foreign alloy atoms naturally diffuse toward the strained lattice space surrounding a dislocation, forming a dense precipitate cloud. When a new force is applied, the dislocation cannot immediately glide. It must be forcibly torn away from the binding effect of these foreign atoms, requiring a significant initial spike in force to get moving again. The behavior of solid metal is a tightly governed system. The Taylor-Arawan equation dictates the flow, the Frank Reed source manufactures the defects, and internal obstacles provide the resistance. A material's ultimate strength is never a single static property. It is the grand statistical sum of billions of microscopic dislocations fighting to move, multiply, and overcome each other within a rigid atomic lattice.